Hey everybody, this is Mike Bartles from HEC. Within this video, I'm going to introduce FEMA's Future of Flood Risk Data Initiative, or FFRD. This presentation builds upon several previous lectures that are a part of this class, including Monte Carlo analysis techniques. You should notice several tools and techniques that you've heard before being used here. This video is part 1 within a series of videos devoted to this topic. As an overview, I'll present some background information pertaining to the FFRD initiative itself. I'll also provide details related to the objectives, methods, data, and modeling approaches that make up this initiative. But before we get started, if you know which dam this is, please write it in the comments. FEMA's Future of Flood Risk Data Initiative is grounded in 4 key objectives. First, to shift from a binary hazard approach, for example, is your house in or out of a certain floodplain, to a probabilistic one that depicts hazards in a graduated manner. Second, FFRD aims to modernize FEMA's management and delivery of flood data through the creation of dynamic and flexible services and tools. These resources should empower stakeholders in the private sector and local, state, and federal government entities who have a role in both development and deployment of such tools. And finally, increasing access to rich hazard data should ultimately drive risk-informed mitigation, planning, and insurance actions. Together, these 4 objectives can drive a more risk-informed national flood insurance program, one that works for many types of users and decision-making scenarios. In support of FFRD, USACE is collaborating with FEMA to provide a methodology recommendation on the framework modeling and data service capabilities, allowing other federal agencies, communities, and individuals to leverage these models and explore structural and non-structural measures for flood risk mitigation. Now let's talk a little bit about analysis frameworks that are part of FFRD. For inland flooding sources, in the past and up until recently, much of FEMA's analyses have been based on 1D hydraulic modeling, where cross-sections are relied upon to define floodplain characteristics. FEMA typically analyzes the most hazardous flooding sources in the watershed and have covered more than 1 million miles of river and stream nationwide following this approach. As FEMA advances into the future, FFRD will continue building on what they've started and will leverage more 2D modeling approaches that are able to analyze more flooding sources within an area, both fluvial and pluvial. Some of this has been implemented and can be seen through statewide base-level engineering studies. Even so, historically, most FEMA analyses have been event-based, and that they've traditionally analyzed only a handful of very specific flood events, namely the 1% annual exceedance probability, and a few others, in large part due to the connection to the regulatory and statutory requirements. As FEMA advances in the future, their analyses are going to look more different, and that they will be based on probabilistic methodologies, whereby they evaluate the flood hazards for many different flooding scenarios across a wide range of storm probabilities, intensities, durations, and temporal distributions that a given watershed might experience. How can FFRD information be used? FFRD models and data will be accessible to the public and support a future federal model repository serving both flood data consumers and producers. Also be recreatable by the public to show alternative structural and non-structural measures, or allow for local refinement of the models. They will be applicable for all watersheds within the U.S. and its territories, despite differences in methodologies or local conditions, and they'll leverage data from federal partners like the United States Geological Survey, USACE, and the National Oceanic and Atmospheric Administration, where possible, and contribute to national level datasets with newly generated data. The generalized modeling approach that is going to be used within FFRD analyses includes generating storms, simulating the precipitation runoff response within HMS. Outputs from HMS are going to be used as boundary conditions by both ResSim and RAS. ResSim needs time series everywhere, and RAS needs excess precipitation grids and baseflow time series. Then, simulate reservoir operations within ResSim. Reservoir outflow time series from ResSim are going to be used as boundary conditions by RAS. Compute inundation depths, extents, and arrival times within RAS. 2D simulations are going to be used to compute the required hydraulic outputs throughout the entire modeling domain using excess precipitation grids and baseflow time series provided by HMS and reservoir outflow time series provided by ResSim. Then finally, we compute consequences for each structure in the modeling domain using the outputs provided by HEC RAS. Now, in order to estimate probabilistic flood hazard estimates with uncertainty, many iterations within a Monte Carlo framework is utilized. So one of my favorite quotes is that of Sherilyn Kenyon: "If brute force doesn't work, you aren't using enough." This applies very well to the situation, as we use a lot of brute force to simulate upwards of 1 million events to adequately describe flood hazards within a watershed of interest within FFRD analyses. But how should we simulate plausible meteorologic boundary conditions in order to derive graduated risk for all locations in a watershed throughout CONUS? Commonly, simple analyses are going to begin by sampling from an input precipitation frequency curve in order to construct a storm event. A random number is generated and then assumed equal to the AEP of interest. Then a precipitation depth is inferred for that AEP. However, how do you convert precipitation frequency curves from point estimates to areal estimates, which require depth area reduction functions? These functions are dependent upon the watershed location, analysis point, storm type, storm magnitude, and so many other considerations. Using them introduces another significant source of uncertainty and requires many, many iterations to adequately sample. Also, how do you distribute the sampled and reduced precipitation depth in time and space? For nearly all watersheds in the US, storms are incredibly heterogeneous in both space and time, and that is an even bigger source of uncertainty. There's got to be a better way than that process. In fact, there is a better way, and it's called stochastic storm transposition. In this video, I introduce FEMA's Future of Flood Risk Data initiative and the partnership between FEMA and USACE that is working to develop those tools and techniques. In subsequent videos, I'll talk more about the storm generation methods that I just talked about that are being used within FFRD analyses, as well as an example FFRD application. Thanks for watching, and I'll see you in the next one.